All right, so now we'll practice a little bit more with vertical asymptotes. So we're given a graph over here on the left-hand side in number 2, and we want to match this with our functions on the right-hand side. So starting with a, f of x equals 2x over x squared minus 4x plus 3. If I wanted to find the vertical asymptotes, I would set that denominator equal to 0. So x squared minus 4x plus 3 equals 0. If I factor that, that would give me x minus 1 times x minus 3 equals 0. Setting each factor equal to 0 gives me two vertical asymptotes, x equals 1 and x equals 3. So those are the correct vertical asymptotes for that function, but we don't have a match on our graph, right? So no match. Okay, for b, looking at my denominator, to find the vertical asymptotes, I would set x squared plus 4x plus 3 equal to 0, x plus 1 times x plus 3 equals 0. Set each of those factors equal to 0. If I set x plus 1 equal to 0, I get x equals negative 1. X plus 3 equals 0 gives me x equals negative 3. So these would be the vertical asymptotes for that function in part B. Again, we don't have a match with our graph, so no match. All right, so hopefully C works out. We're going to set our denominator x squared plus 2x minus 3 equal to 0. X plus 3 times x minus 1 equals 0. Set x plus 3 equal to 0, and we get x equals negative 3. X minus 1 equal to 0 gives me x equals positive 1. So there we have a match, right? So we've got those vertical asymptotes at x equals negative 3 and x equals positive 1. X equals negative 3, x equals positive 1. So this guy's our match. Okay, so that brings us to kind of a weird topic. So this comes up with our vertical asymptotes. So there's something called the whole of a rational function, finding wholes in a rational function. All right, so here's an example of a function that would have a whole, a vertical asymptote as well as a whole. So we've got the function f of x equals x plus 2 divided by x squared minus 4. All right, so first, what values cause the denominator to equal 0? So we'll take the denominator, x squared minus 4, set it equal to 0. Factor as a difference of two squares. Set each factor equal to 0, and that gives me x equals negative 2 and x equals positive 2, right? So these are the two values that create a 0 in the denominator. And by the way, just a side note, when you're solving x squared minus 4 equals 0, you could also add 4 to both sides and solve that way, so x squared equals 4. But when you go to take the square root, remember your plus or minus. So that's where you get x equals plus or minus 2. A lot of people forget that step and just end up with positive 2, but of course there are solutions there. So just keep an eye on that. Okay, super. So we've got x equals negative 2, x equals positive 2. If you look at the graph over here, there's just one vertical asymptote drawn at x equals positive 2. So that's your only vertical asymptote. Okay, so what's happening at x equals negative 2? It's maybe hard to see if you zoom in a little bit. There's a little open circle at negative 2, or you could call it a hole, right? So there's what's called a hole at x equals negative 2, meaning the function, let me write it this way, the function doesn't exist there. Function does not exist there. Okay, so visually, this is our hole versus our vertical asymptote. But why is that the case? Why is x equals 2 a vertical asymptote, but x equals negative 2 is a hole? How do we know that? So let me just pull this up also in my graphing calculator, because we might be able to play around with that as well. So I'm going to graph x plus 2. Notice I put parentheses around the numerator. divided by parentheses x squared minus 4. Make sure you contain the numerator and denominator. So again, you can see on our graphing calculator, you can see where that asymptote would occur at x equals 2. And even if I use the trace function, like if I type x equals 1, for example, I get y equals -1. If I type x equals 2, on my calculator it says overflow error for y, but on yours it might just be blank, or it might say error or something like that. But there's some sort of error when you type in x equals 2, because there's a vertical asymptote. If you type in x equals -2 using the trace function, we get another error. So again, your calculator might just be blank for y. It might show an error message. On this map calculator, it's showing not a number. So x equals 2 was the only vertical asymptote. What happened at x equals -2? Since the original rational function is not in reduced form, there is a hole at x equals -2. Okay, so let's take a look at that original function. F of x equals x plus 2 over x squared minus 4. I could factor in the denominator to get x plus 2 times x minus 2. And when I factor, that means that I can cancel out the matching x plus 2 factors from numerator to denominator. So that leaves me with my simplified function, 1 over x minus 2. So after my function is simplified, if I take my denominator and set it equal to 0, that gives me x equals 2. That's my vertical asymptote. The factor that got canceled out, the x plus 2, anything that got canceled, if we set that factor equal to 0, that's what creates the hole. Okay, so a factor that still remains in the simplified denominator of a function, that factor produces your vertical asymptote. Any factor that could get canceled out in the simplification process, you can still set that equal to 0, but that creates a hole in your function. So to find the hole, to see where it would be located, if you find f of -2 using the simplified version, 1 over -2 minus 2, so using this simplified version, if the function existed at f of -2, we would get the y value of -1/4. So that's where that hole is drawn. So the hole appears at -2 and then -1/4 for y. But the function doesn't exist there, but that's where the point would be if it existed. That's weird. I know what I just said. Weird, but true. All right, so the hole is located at the point -2, -1/4. Okay, so when do holes occur? When your function can be simplified, when you can keep going and put your function in reduced form. The denominator factor that you cancel out produces a hole. Any factors that are still left in the simplified function's denominator produce a vertical asymptote. Okay, so just as another example, where is the hole in the graph of f of x equals x squared minus 9 over x squared minus 3x? So let's factor this denominator. So x times x minus 3. So, draw down there. So our function, we could rewrite this as x squared, or sorry, I'm also going to factor in the numerator, x plus 3 times x minus 3, right? So we've got x plus 3 times x minus 3 over x times x minus 3. So that's still the original function, just in factored form. Now notice that x is not allowed to equal 0 and x is not allowed to equal 3. The function doesn't exist at x equals 0 or at x equals 3. But as we move forward, I can cancel out those x minus 3 factors, and that leaves me with my simplified function in reduced form, x plus 3 over x. So because that x remains in the denominator, after I simplified, x equals 0 is my vertical asymptote. So x equals 0 is my vertical asymptote. And then that x minus 3 factor, if I set that equal to 0, that gives me x equals 3 is where the hole in the function occurs. Okay, so where's the hole in the graph of f of x equals x squared minus 9 over x squared minus 3x? The hole would exist at x equals 3, and if you want to find where the y value would be if the function existed at that point, you can use the simplified version of the function. So putting in x equals 3, we'd have 3 plus 3 in the numerator, 3 in the denominator, 6 over 3, which gives me 2. So the hole would occur at x equals 3, and then y would be 2 if the function existed at x equals 3. And we represent that with an open circle on the graph. We represent our vertical asymptote with a vertical dashed line.